Hey everyone, welcome back after the Christmas or winter break. Hope you relaxed a bit and have enough energy to now start again in the new year. So today we will look at bias and fairness, especially with regard to causal models and causality. And maybe before that, so to give you a brief overview, so we had some Polian causality basics, then something on representations and machine learning. And now for the last part, we will look at, I've titled it applications. So it's more of what can we do with causality? Where can we apply it? What are maybe alternative perspectives or representations that also work with causal quantities or models that maybe not align with the Polian causal framework. And so in the end, we will have a last lecture where we do brief recap and have time for also questions. So yeah, in 2 weeks, we will have the lecture survey. So, I mean, it's rather late this semester, but maybe we can then improve things in the next iteration if you have any suggestions. And then for the last lecture before we will release an exercise exam that will be roughly like the scope of the real exam. So you can have a look at that. And again, remember it's a 3 CP course. So it's not like an ultra hard, you need to like get everything that we talked about like in super detail. But yeah, I think there you will have like some comparison what to expect in the end. So yeah, and then again the exam date, it's the same day, but we shifted it a bit back because of the computer vision 1 exam for those people that like really want to take both exams at the same day. So I think there might be an hour or half an hour between the exams. So I hope that's enough to shift rooms in case anyone needs to do that. Okay, so then let's start with bias and fairness and maybe look at some examples that you might encounter in real world prompts, which is basically that there are language models and you have some sentence and you ask like for specific words in a sentence, like pronouns for doctor or secretary, and you get some results from your language models. So this work is like a few years old that really did this, but even if you typed it in today, you would get similar results. So these models have learned from the data this bias that a doctor is usually male and a secretary uh, usually female or woman. And so you get these biases, whereas like from a really like objective, uh, like like a neutral perspective, there should be no differences in the gender, right? Like each, yeah, whoever it is, everyone can become a doctor, everyone can become a secretary. So these models like introduce biases, and this might, I mean, one can say, okay, it's reflecting the real state of our system at the moment. There are these biases, but consider that you might want to counteract them, or you are like giving like opening job positions where you use these pronouns, right? So you're reinforcing or like um, yeah, you're reinforcing maybe these biases by putting these pronouns in that way in texts if you are not careful, or at least the language models will do that for you. So that's maybe one problem. And as I said, we want to have models that may not replicate these biases, or at least that are aware of them so that we can counteract those. And this not only goes for like general applications like normal text writing or whatever, but like we have a lot of biased data in medicine, jurisdiction, employment, finance, everywhere where we have historical data that might be biased, or where we have legislation that also forces us to adhere to some standards in terms of fairness. So yeah, in some cases, for example, jurisdiction or finance, there might be actual laws that require us to like document our efforts, and also to not discriminate against particular groups of people, for example. And so since we are probably going to train such models at some point, we might want to look at different biases that can get introduced to those models. And I think one of the most common one that you get taught is this bias variance trade-off, which is like usually taught from a really like technical point of view, where we say, well, if I have a very simple model, it probably learns the mean and a bit of variance. If I have a very complex model, it might not be that biased, but learn the real details of my data. And by moving or increasing my complexity of the model or decreasing it, I can somehow transition between these kind of biased, maybe more robust mean prediction and a more complex detailed prediction. And yeah, I mean, this is somehow mostly about optimality and predictive power of those models. But of course, if we take those models then to make decisions, it has an impact on the people that we take decisions over. And as we saw before, then we have these observational biases, as I also showed you in the LLM lecture, where we saw that even in objective like causal reasoning, LLMs can adopt like data bias. Yeah, it just the models replicate whatever we teach them, right? So it's either we correct our data and somehow like debias it, or we need some ways to post hoc adjust for those biases that they may have learned, or maybe even in the first place, yeah, find that those biases are there. Yeah, and this goes in the same direction, right? It's like models adapt cognitive biases, so everything that humans do and then write down will eventually end up in our training data. Yeah. And of course, we want our models to be better than us in terms of fairness, predictive power, whatever. So maybe another example to show you some images. It's always the same scheme, I guess. So it's a stable diffusion model from some years ago. I believe it was stable diffusion 1.5, if you know that. So the task was to generate a photo of a firefighter. And what you see is that all the generated photos are like white, male appearing persons, usually in I think it's a US outfit or uniform. And maybe we want to have some diversity. So the question is, if I want to maybe diversify my fire department, I maybe do not only want to use those images that I generated, but maybe I want to have some diversity in gender, maybe in skin color, whatever, like ethnic background, you name it. So the thing, or what people from our lab then did, is that in those models, you can identify certain directions for certain appearances, for like male, female, whatever, and you can basically geometrically add those vectors to your normal generation. So it's this, if you think about this common example, what a man is to a king, a woman is to a queen, and you can find those differences or these relations also in the latent space of your large language models, of your diffusion models. And you can then possibly, once you have extracted those concept vectors, you can basically add them to your generation to diversify your images. So basically, you then sample from those latent random vectors and add them. But we won't go into this because this is more like how to work with these models, how to modify them. But we want to look at the causal aspects of fairness and bias. So again, it's most of the time historical bias, where, for example, man had better access to education in the past. So if we were to look at all the maybe academic data from schools and whatever of the last 100 or 200 years, our models might see those data, see that it's maybe male dominated, and might get biased by that. And how do we counteract that? And in this scope, there are a lot of other biases. We will look at a few of them and mostly try to figure out how to counteract them. But sampling bias, observational bias, it's really what is in our data. Then, for example, model bias is, as I said, this bias variance trade-off. And then a lot of other things like how do we do our measurements, some outcome biases, again, how get decisions justified post hoc, for example. It's a lot of stuff you can deal with if you got some data that you might need to be aware of. Like usually it really depends on the task and the data that you got and how important or how severe those biases are. So, and this lecture, it's not only about bias, but also fairness. And these two are obviously somehow interlinked because every biased decision that we take might also not be fair, or the other way around. Maybe if we take unfair decisions, they are in a way biased. So if we somehow can measure bias, we might get to notions of fairness. And so it's also something about optimality. So usually in ML, we train our models to be optimal with regard to some prediction. But if I do that at a bank, I could maybe boost my profits by not giving loans to poor people or to some subgroups. So I might deny them any participation in the finance sector, which is obviously unfair and might also be prevented by law. So the problem or the good thing here is that it's usually not okay to just train our optimizers to just maximize our profits. But here we really need to take care of that. We also are fair and do not discriminate against certain groups. Yeah. So maybe we are looking now at biases in causal models. So far, it was more of a general application thing, but we have seen graphical causal models, like structural causal models, and we have also seen how to estimate causal effects within them. And maybe, for example, in the front door or backdoor criterion, we've also seen that we usually need to adjust for certain factors, for confounders and so on, when doing regression or estimating some effects, because otherwise we get these biasing factors in. And causal models, or generally structural probabilistic models, are somehow white box, which is really nice because we can like see how effects travel, how factors are related, and that usually helps us to estimate where biases come in. Yeah, basically it is that we can now apply our whole concept of do calculus that we saw before to get maybe the correct estimate of some variable onto another without having other influences there. And just as a reminder, so of course it can be much more complex, but like common things that you encounter might be either confounding paths, so this set variable that confounds x and y. We can have collider paths, so basically some variable c that we condition on during our regression, and that then also induces a bias because yeah, it closes this collider, graphically speaking. And then again, we can have the direct causal effect that we usually want to have. And most of the time, we might also be interested or simply interested in the total causal effect, which then includes all those indirect paths via some other variables. And here it might also be that I mean, it really depends on our causal model, right? So if we just were to marginalize A, this effect would simply go into the direct causal effect there. But yeah, direct causal and indirect causal effects are those ones we are interested in, and we want to correct or like exclude all the other paths that are non-causal. Yeah, and again, doing so or failing to adjust for those will give us some biased estimate. And the thing here is that it's not only about like doing the correct causal inference within our model, but be aware that like in general real world settings, oftentimes it's very difficult to get hands on those on the right causal graph, right? So in economics, you have a lot of different factors and effects that can play into your model and that you are trying to correct for. So if you are in a very like synthetic or lab setting, you might know the true causal graph, but otherwise, please be aware that there might be like other nodes that you don't see. They might interact somehow with each other. And it's usually your tasks or that of like economists, statisticians, whatever, to like get hands on those data, and also to estimate how severe these effects will be, right? Like there might be like 50 smaller effects going on that might not be relevant or might not be relevant individually, but we need to account for them in total. And these kinds of things that we will not talk about here, but we will look at like the assumption or make the assumption that we have the true causal model, right? Because otherwise basically everything can happen, right? Then we need to make some additional assumptions or somehow need to say, well, all the exogenous noise is somehow bounded. And that usually requires expert knowledge. So, but one example that we often see, especially in ML trainings, is some sort of collider bias or Bergson's paradox. So the thing is, usually we take some data set and apply to our language models or to our machine learning models. And somehow before that, we like someone went and searched images maybe of birds and wanted to diversify the data set a bit. So the data set now consists of like common bird images and rare bird images. And for example, here it's the scenario of a like photo gallery or something that says, well, if I have a common bird, where I have a lot of images, I will include this image if it's like really high resolution, because I have so much of them, I somehow need to filter. And for rare birds, because I have so few of them, of those images also, I will include everything. Like even if it's the most low resolution image that I get, I will include it just to have some data, right? And so we might want to then use this data set to train our models. And if we do so, our neural nets might learn some like meta reasoning or like some spurious correlation, which basically says, well, if I have a low resolution image, it's probably a rare bird, so I want to include it, right? So if I'm not careful enough, my model might be biased to include all the low resolution images because it was a good indicator for detecting rare birds. And this then might be a problem if we want to apply to our website, to our data selection process, because we learned those spurious features. And like causally speaking, it's really this causal model. So we have like X, for example, are those common bird images, Y are those rare bird images with like high or low resolution. And Z is our data selection process. And what we then see in the end, right, is that Z is basically an OR relation, that either it's a common bird image with high resolution or a rare bird image. And in the end, in our data set, we only get those images, or we only observe those images that are included in the data set. So we observe this subset. And basically, what happens then is that we expose our models to a data distribution that is basically the outcome. So it's the prediction conditioned under these sets equals 1. Basically, what this means, or what we could have looked at, is that if we have a common bird image, so we have X equals 1, then because of this OR relation, this image will always be in the data set, right? So we have a high resolution image, for example, and because X is already enough to take those image into the data set, we are looking at the probability of Y being 1. And in this case, like we get the probability of Y being 1 just being the probability of it being 1 independently. So it's marginal or base probability. But in the other case, so this is the trick of maybe explaining away, that if we have X equals 0, we require Y to be 1, because otherwise we wouldn't have this image in our data set, right? Because we only observe those data where X or Y is 1. So if we know X is 0, then the probability of Y needs to be 1. Really, we have this like unbalance somehow in our data. When one case, it might be that we observe a rare bird if we have a high resolution image, for example. But if we have a low resolution image, our model knows, like, or at least thinks with certainty, that we have a rare bird. So it might classify it always like this. So, I mean, probably you have seen it in other courses already, but this is then a problem if we select data sets based on quality or interest. We need to be careful that we don't get like confounding in a way that other factors like that are not our target variables might induce those biases, which is then based on the quality or maybe the format of some of those images. And the Other thing that we could look at is the Simpson's paradox. So this is an example from the Book of Y, where you say, well, I want to do some regression on the hours of exercise, on the cholesterol levels in the population. And what I might observe is that somehow the more people exercise, the higher their cholesterol levels are, which might be a bit weird. And here, just a disclaimer, I will have it on the slides later. It's sort of like synthetic example, but to prove the point or show the point. Basically, has someone an idea why we could see such an effect? Maybe we have missed something, maybe there's something wrong with the data. But this is like really we got some data set, hours of exercise, cholesterol levels, and put a linear regression on it. So maybe the thing here could be that we forgot actually to account for age. So what we got or looked at was the joint population, and as maybe expected or what we would hope for is that if we exercise, the cholesterol levels go down because maybe people are more healthy. But the problem is that the overall population is heavily influenced by age. So the different age groups basically induce this like overarching bias, these positive correlations. But if we were to like condition on age or like say age groups in a range of 10 years, we would see that actually within each of those groups, exercising really helps. And this is like, again, this thing that if we have this confounding model, so here what I said, right, it's somehow a bit artificial because it somehow assumes that with age people maybe exercise more because their doctors tell them to do so or something. But in any way, if you get those structures, you might run into this paradox where yeah, like regressing on the joint distribution might give you incorrect estimates or coefficients. So again, yeah, the real effect is exercise on cholesterol levels that we want to have, and we need to account for these vector paths that we need to exclude. Yeah. So far, I think this was more about like classical biases and regression and causal models. But now we might want to maybe look at fairness metrics. So what does it mean to be fair, and which kind of definitions are there, which kind of like maybe loss functions can we apply? And what we somehow talked about already for causal models is that we might not be able to observe all the data we have. We might not be aware of all the data, but in fairness, like in the domain, what is commonly done is that we want to take some decision which should be fair with regard to some construct, to some like quantity. So this is usually defined in this sort of construct space. Then we have an observed space, which is really the data that we are able to observe. And then we have a decision space. Basically, this tells us, okay, if I have individual entities, like individual persons from which I observe my data, how do I rate or classify, like which label do I assign to them? And how like are those entities related to each other in terms of like distance metrics? So maybe we embed them in some vector space. take all the observational attributes that we have from them, then add the decision attribute there and compare if maybe entities that are closer together in this space get the same or get different labels assigned. And yeah, so the thing is, usually we don't directly observe the attributes of the construct space that we want to take decisions over. So we need to have some observations as proxies, which basically is maybe we want to take decisions over the performance in college. And as a construct to like estimate this outcome, we might uh, want to look at success in high school, and oftentimes this is measured via the GPA or like some other performance or metrics or grades. The same thing is okay if I want to know if my employee will be productive. Maybe I want to take a decision over the knowledge of the job that he or she has, and maybe an observed number that we can easily get is the number of years of experience in that job. Again, always there is this difference between the construct and the observed space. So what we really would like to take a decision over and the actual data that we can observe, that we have access to. And yeah, it's really up to somehow an expert or you as a designer of this study or experiment to really think about it. Is the number of years of experience a good indicator for knowledge in the job, or is the GPA a good indicator for success in high school? Right? So maybe it's this thing of, do I really need to like limit the number of students based on their like previous GPA? Or am I able to give everyone access and filter out later maybe? Of course, it's always about costs and a lot of other factors, but yeah, I think this is like the most general scenario that we can think of. Yeah. And again, as I said, the whole thing here is that usually we need to use proxies because like the real construct that we want to take decisions over is usually not observed directly. And so this scheme or framework with constructs, decision space, observed space that we talked about, this paper then introduced a sort of like epsilon fairness, which basically tells us, okay, if I have all my attributes and let's say for now I'm able to like learn or define some distance metric over all of my spaces, at least in theory, some decision is fair if the distance in my prediction space, so the distance in the outcome labels, is smaller than some epsilon, in the case that also the samples I gave in are like close together. So basically it really tells us, okay, if I have individuals which lie close together in some space, I would like to have them to have the same label in the outcome, right? So it basically is some associational measure that just tells us, okay, similar individuals receive similar outcomes or labels. But I mean that's nice to state, but the thing is, yeah, it's a bit of a trick or a cheat because like who tells us how to define those distance metrics, right? Because even like in like standard Euclidean spaces or something, maybe our attributes might be scaled to a different degree. Okay, we might normalize them, but still, is every attribute equally important? Who decides that? And like, yeah, it's the definition itself is nice, but the question here is how do I define those distance metrics? So be careful if you want to apply this, you need to be sure that like your distances are somehow well calibrated. But again, I think it's a good thing to think about. Really, I guess that's what we want in the optimal case. If we have those metrics, maybe similar individuals should get assigned the same outcome. So in this kind of setting, usually what is happening is that people define protected attributes, especially in like legal domains or applications, where they say, well, you can't use the age, the cultural or ethnic background, sexual orientation, or the religion or belief of a person to take decisions in maybe finance or employment. So whatever happens, you cannot use those attributes to make a decision. So they need to be excluded from your decision process. And basically, what this means in terms of model training is that we somehow want our prediction y hat to be invariant of all those attributes. And so what we could do is, okay, in the first step, we define a very simple metric, which is the demographic parity, where we say, well, that's somehow easy. I look at all the data, but I require my model, if I were to change or randomize those attributes, that the outcome should be the same, right? So maybe I take all my data, and so for applicants, I just give the parental status or whatever into my model, but then I maybe duplicate all the data and I flip their parental status. And in the end, I take a loss term that tells me, well, if you take a different decisions between people with, like the samples with and without parental status, then you're somehow biased. So yeah, again, I discussed some of the example. It's about hiring, it's about granting loans, and so on. So basically, what this metric does is that it somehow divides particular entities or this whole data set into subgroups that have the same setting of protected attributes, and it requires that the outcome or the decision that we take over those subgroups that they are really the same or have the same probability at least. Yeah, so exactly for then defining or using it in training, you do not take the equal sign here, but you put a minus and then measure like the difference and punish your model for that. But somehow this can be unfair if we think about it, right? So let's say we have some groups of people that we want to grant college admission to, and they have like a particular but different set of protected attributes. And for the first group, we just select the 50% most qualified people that we get according to some metric. But for the second group, we just randomly select people. So eventually, group B will be less successful because, yeah, somehow we just took random persons that might be more unlikely to not succeed. So somehow this metric balances some aspect of our decision process, but it is still possible that we take unfair decisions, that we like either accidentally or like purposefully bias our outcome. Yeah. And one thing, if we think about how to fix that, might be that we looked at the probability of the outcome. But here in these expressions, you do not see like the original ground truth label, right? We don't look at the actual underlying y that should be there. So in some scenarios, we might not have access to it, but again, maybe we have some proxy variables that tell us how successful people will be, like looking at their GPA, for example. And somehow we want to include that in our fairness metric. Yeah, and let's say we do that. So it's a simple addition. We just condition on, okay, according to the GPA, are they like above a certain threshold? Are they in the top 50% of the cohort? And we just expand both expressions to condition on that. And now we require that both of those terms need to be the same. So it's quite simple. It's called equality of opportunity. So really, if you fulfill the requirement for entry or something, independent of your protected attributes, you should be given the same chance or same probability to apply for college, yeah, get a job, get a loan, whatever. But still, this, yeah, this might not be enough, right? So what we looked now were like the true positives, because we looked at all the people that were like truthfully assigned a label in the positive outcome. But maybe there is also a cost, and maybe also a really high cost to false decisions. So maybe if we take decisions if people get out of jail or not, like okay, it's nice if we like if everyone has the same chance to get out of jail, but maybe one group is discriminated against because if you like have really high false positive rates for some subgroups, we might overpunish for that group. And again, under constraints, it's maybe the same. So we might have like true positive rates for all of the subgroups that are the same. But then there is always a bit of noise, right? Your decisions are not completely correct. And we do some like false positive decisions of group A that gets admitted more often for some reason. And because maybe at the university we have a limited number of seats, then it discriminates basically against all the other subgroups, right? Because they are getting their like seats taken away from. So those subgroups are underrepresented again. And the thing here is then really that this leads to this equalized odds metric, which basically tells us, well, we just should not look at only x equals 1, but we look at both cases, right? Like we want to require the same probability for those people that get accepted or where we have a positive label, as well as all those people that we reject that get a 0 or negative label. But yeah, so I think this is quite okay to think about this, but somehow all of this is more of a correlational thing or associational thing, right? So we are looking at probabilities over some subgroups, and like from a overall perspective, from a global perspective, this might be nice, but it might not help you from an individual perspective, right? So it's cool for the university or your employer that that now all these odds are equalized, that everyone has, or like these groups have the same probability. But if you get like your rejection letter from the university, you might ask, okay, was I personally maybe somehow discriminated against? Would I have been accepted if I had been a different age, came from a different part of the country, whatever, right? So all those previous metrics looked at subgroups as a whole, but maybe we want to take a more like individual perspective and think about that. And yeah, if we want to think about this would have been accepted if I had been a different age. That's like a really classical counterfactual question, right? So the decision might already have taken place. And now I want to track back all the attributes, all the factors that were relevant for this decision. I change maybe one of my protected attributes and then rerun this decision process again. So this is like the classical three-step procedure we saw for counterfactuals. So this is like inherently causal in a way. And yeah, that's what we will be looking at next. Again, just to have it on the slides. So the previous metrics were about like groups or like subgroups that need to be treated equally. And now in the next counterfactual fairness metric, we will look at individuals and how to show that every individual on their own might be treated equally or might not be discriminated against. So yeah, before the short break, we talked about notion of counterfactual fairness. So basically that like from an individual perspective, we would like to consider outcomes under the situation that maybe retrospectively some attribute was changed, some protected attribute. And what we would like to see is that it does not like flip the decision for some model or some process to be fair. And so what we saw is that this is then somehow really, or can be framed in terms of counterfactuals. And I think we briefly had this notation in previous slides or also in the first exercise, if I remember correctly. Basically, what we can write down now is this kind of counterfactual fairness, which really basically means, well, I, of course, condition on all my standard variables, especially I condition on all my protected attributes. Then I do all this backtracking business, right, to get some exogenous variables, which somehow are like defined via my causal model. And then once I have those exogenous variables, I intervene on my protected attributes. I assign them a different value. And then I like forward propagate all these exogenous factors through my model under the intervention that I have done. So yeah, this subscript A equals A dash really means, well, I made an intervention in then the forward pass in this third step. And yeah, so the thing here is this is really then not about like a subset or a group of people. I mean, obviously you can also view it like statistically probabilistic and do it, but like these counterfactuals, they are about individuals, right? For every entity in our population, I can go and check and say, well, for that individual, I do my backtracking, I do my intervention, and I compare whether under this counterfactual perspective, my original classification is the same as the one under my counterfactual imaginary scenario. So this then again, we can maybe create a score out of it by like summing up all the differences that we observe. And in the best case, of course, we don't observe any individual in our prediction under this metric. But yeah, I mean, the example is the same about opportunity for college admission. So every individual, if they may be asked, sometimes you are like companies or like organizations are required to disclose their decision process, at least to some degree. So every individual could go have a look at their maybe causal model, at their decision process, apply this metric, this fairness, like notion, do backtracking, do this forward pass, and see, well, it's not only the subgroup that I'm in that was treated fairly, but like for me personally, I don't know, some professor didn't like me and rejected me, but no matter what happened to all the others, the outcome for me personally, for this particular individual, did not depend on the protected attributes. And that's, I think, what we would like to have. Yeah, and because we had it in the second, I think, equalized odds metric, again, here we do not look at the ground truth label. So this might again open up some problems, right? We could be somehow again arbitrarily wrong. But what it tells us also, or like leaving this away, tells us, okay, we cannot be biased by some ground truth, right? Like all these historical biases, observational biases, whatever, like our fairness metric at least does not depend on this label. And then, of course, if you're a training model, usually what you do is some sort of trade-off between optimality and predictiveness of your model and the counterfactual fairness. So maybe you just construct a loss where you say, well, one is my accuracy, and the other loss term is this counterfactual fairness metric. I just add them together, or like via some sort of writing. If you're in a like some other setting like optimization, you can also take these fairness constraints as like hard constraints, right? Where you say, well, I want to do some like linear optimization, and every of those things here for every individual puts one constraint into my model space. Yeah. And so, yeah, we can apply this to some neural networks, but we can also really do it just in a causal model. So let's say we again have this somehow biasing or confounded graph. We want to have the effects of X on Y. We have some confounder that we observe, and it's a child of some protected attributes. And what we then really can do is do our vector adjustment, which from what we already know, like really gives us the effect of X on Y. So it's independent of Z and therefore especially independent of A. But if we look at this expression, right, it's somehow some, not say weird stuff, but like it's not like some simple probability that we compute. And what this basically means is that only because we are able with our causal model to estimate and debias this effect does not mean that our neural network, if we just plug in, well, X and Z into it, that it doesn't learn the correct distribution, right? Because this thing here, this neural network, just learns some functions of X and Z, and there isn't or doesn't necessarily need to be a like one-to-one correspondence between our causal variable and maybe some sort of adjustment set that we have identified in our causal model. And our neural network, if we then take our X variable and all the adjustment set, right, it doesn't mean that our neural network predicts the right thing, because this process or this estimate that we have here for our causal model, it is really dependent on the graphical structure of this model and requires a lot of sub-steps, right? Like different probabilities, marginalizing out the set and so on, which is like not trivial and certainly not just simply learned by neural network, which is mostly simple regression in that regard. Yeah, some very simple argument is, right, it can't differentiate between X and Y, X and Z, like all the inputs are like treated equally. And if we were to give X and Z in there, the model will always, or mostly always, predict the same thing. But here, maybe our graphical structure changes, our graph changes somehow. That would mean our estimate changes, but our neural network might still predict the same thing, right? So it doesn't know of this graph structure, it doesn't take it into account. Yep. So from what we have seen, I mean, yeah, it's cool that we have structural causal models, all these graphical representations, but let's be honest, like if you have real applications, what most companies do is still they train neural networks. I mean, we should push more for graphical structures, but in reality, we need to take some action to at least make sure that if we have our causal models, that we get some insights from them that help us to train networks that are fair and make the right decisions. And for that, in this paper of counterfactual fairness, they proposed a lemma or a criterion that says, well, if I take for my model training only variables that are non-descendants of A, then my training will be fair. And we will see an example of that in the next slide. But like informally, if you think about this, or maybe remember the graph we had in the beginning with the confounders and colliders, basically what it means is we need to condition on confounders. And the problem there is we need to marginalize out all of these effects and whatever. So that means we cannot have any variable or any protected attribute that goes like as a confounder, as a parent into our attributes that we take decisions over, because we cannot do this marginalization or confounder adjustment in our neural networks, or they just don't do it. And then the other way was a collider, where if we close that one, if we include those variables, they give us this Pearson paradox, right? This collider thing where now somehow by conditioning on a collider that is somehow related to some of our prediction variables and some of the protected attributes, we close this correlational path in the network. And now our network might take some decision that is somehow associated with one of the protected attributes. So by excluding all of the descendants of A from our predictions, we make sure that our model cannot associate any of those protected attributes with the prediction. And again, this depends on the graphical model that we assume, like the structure, and it's a very conservative thing to do, right? Because it excludes a lot of potential variables that might be helpful, that we could have used if we were in a causal setting, like in a causal graphical setting, where we just could have corrected for confounding and so on. But here, if we do it via like associational learning of neural networks, we need to exclude really all of those variables. And in some cases, then there are no variables left to predict or like to base the prediction on rather. So yeah, this was a lot of like theory and talking, but there is a really nice example, I believe. It's really this confounding, this collider thing, which says, well, we have some cultures, A star, which maybe prefer red cars, and we are an insurance company, and we want to estimate the accident rate, maybe to base our pricing on that. And for that, we have collected some data, maybe on the driving style, maybe we know the registered cars, we know the car color, and so on. And now we take all of these A, X, and U and plug it into our neural network. And I think it's clear what's happening, right? So this one culture that prefers red cars, they drive maybe the same as every other culture, like every other assignment of A. But maybe people that drive a bit faster prefer red cars, or I don't know, right? So we have this confounder, which is car color. And by conditioning on the car color, we now open this collider. So yeah, our model might take the car color as an indicator for driving style, or maybe in a regression, even though we have the driving style, also takes in the car color somehow, like punishes red cars like with an extra penalty. And by that, we discriminate against this one culture, which for some reason that is really not related to driving style, chooses red cars over other colors. So that's bad, and we need to take care of that. Yeah, and basically what this lemma from before tells us, okay, we cannot really take this car color because it closes this path. Yeah, we should not use it in our trend. Yeah, then again, somehow or sometimes you will hear that counterfactual fairness is somehow called fairness through unawareness, right? It really relates to these things that, yeah, we cannot use car color. Of course, we cannot use the cultural background directly to predict the accident rate. So basically, our neural network does not know about all of these attributes, so it's unaware of them. But please do not make the mistake to have the sense that we do not care about this attribute, right? Because as we saw, we really care about them. We just care about them not being present in our decision process. So again, right, it all depends on the causal structure. Even if we, like in the end, in the final training, it's no longer present because the neural network, it just takes all the stuff that we then only give it to it and make some prediction. It doesn't know of causal structures and stuff. But again, we might also, so here is maybe a confounding example, not use zip codes, for example, right? Because maybe historically certain like groups of people settled in particular places. So if we want to have background of a student is a protected attribute, or the background like in general, it might be related to the background of his mother, and she settled in a particular area. So by conditioning on this zip code, we again have this associational link to background, even though we are looking at a non-protected attribute, but still it's somehow related, right? So really, I think counterfactual fairness is nice if we are working directly with causal models. We can do much more. We can do a lot of adjustment if we are assuming we have the right one. So I mean, here it's clear, right? From a like causal perspective or graphical perspective, we see zip code. It should take no role in the decision for admission. So because what we see is right SAT score, at least in this model, if we condition on it, the admission decision gets or becomes independent of everything else, right? It blocks all the other paths. It's really this explicitly acquiring knowledge and looking at these protected attributes that in our final decision, we have this graphical separation in the end. And if we are doing a neural network model training, it just needs to be much more stricter because neural networks don't know about the causal graph. And then again, counterfactual fairness is nice, but as I said, sometimes you're required to also look at like subgroups for legislation or whatever. And it's not only about being fair individually, but being fair with regard to different background, age groups, whatever. And we have a lot of different fairness metrics. Like if you look a bit deeper into the literature, there are like tens of different fairness metrics that slightly differ to each other. And the thing is, many of them cannot be satisfied at the same time together. So really, it's oftentimes this individual versus population level fairness, like this individual versus global perspective. It's then about optimality, like, okay, it's nice if a model is fair, but like if we can take no good decision, what does it help us? Like if we exclude all the attributes, we might not be able to take any decision, which might be even worse than like taking some slightly biased decision, maybe. Or it's also about recourse, right? So maybe we are fair with respect to some metric, but the cost of a mistake in our decision is much higher to correct for some subgroups than for others. And so this puts an additional constraint on how we take our decisions, how our models take decisions, and this might not align with other notions of fairness. So in every case or for every application, it's not that we just blindly plug in counterfactual fairness or equalized odds or whatever, but really every time we have such a thing, we need to identify, yeah, like what are the relevant factors, what are the goals that we want to achieve? Is performance important? Are we like somehow constrained by law or by some ethical standards? And then only really choose the right metric here. But in general, I mean, counterfactual fairness, I believe, is quite nice and intuitive, especially for if you take individual decisions. The other metrics are more of a like high-level perspective that can be used as a sort of soft constraints, I'd say. Yeah, and that's it. Thank you, and see you next week.